Okay, Professor Dolores, did I say that right?
Fine.
Yeah, take it away. We are excited to hear what
All
you have
right.
to say about galaxies near, far, and wherever you are. That's a fantastic title.
Thank you. Yeah. I was in Toronto recently, and so there was a lot of Celine Dion playing, and I figured it was appropriate. So hi, everyone. My name is Mia Delis Reyes. I'm at Amherst College, and today I'll be talking about, I actually realized there's a typo in this title. I'll be talking about connections between local and high redshift dwarf galaxy populations with Hab worlds. But before I get started, I just want to take a quick moment to acknowledge that there are a lot of communities who have helped make this work possible. I think especially as we get closer to celebrating Thanksgiving in the United States, I think I want to take this time to acknowledge that I'm a settler, and I live and work in an area that was built on the unceded homelands of the Pocumtuck Nation on the land of the Norituck people. And then even though we'll be talking about space telescopes for a lot of this talk, I will be discussing a lot of work that's been done with ground-based telescopes and a lot of my work, which has been done with the Keck telescopes. And those observations were really only made possible because Mauna Kea was dispossessed from Kanaka Maoli, or Native Hawaiians. And then finally, especially because we're going to be talking about building new facilities, I think it's really important to acknowledge that there are lots of staff, so not even just scientific staff, but also administrative staff, maintenance workers, janitors, all of these folks who help maintain our science. So I just wanted to take a quick moment at the beginning to acknowledge all of these folks. And then one final disclaimer, which is that I have actually never used a space telescope. So this is a very new topic for me. And so I'm asking a little bit for your patience. It's entirely likely that I'll say something incorrect about Hab worlds or even space telescopes in general. But at the same time, I'm hoping this can be a learning opportunity. As someone who's sort of outside of the space telescope community, it's possible that this could be a good exchange of ideas based on the work that I've done with ground-based observations. Okay, so getting into it, I haven't thought a lot about space telescopes, but I have spent a lot of time thinking about relatively low mass dwarf galaxies. So when I say dwarf galaxies, here I'm just talking about anything that has a stellar mass of less than about 1 billion solar masses. So on the order of hundreds or thousands of times less massive than the Milky Way. And many of you probably already know this, but low mass dwarf galaxies are useful. So sort of from a pure logistic standpoint, they're incredibly useful. There are a lot of them. For every one Milky Way, there's on the order of tens to hundreds of these low mass dwarf galaxies. And they're diverse. So in our local group, if you pick any physical property, stellar mass or star formation rate, star formation history, chemical composition, you can find dwarf galaxies that span a wide range of parameter space. And so that makes them very useful for testing physical hypotheses. And then also compared to more massive galaxies, like if you look at the Milky Way, it has a lot of moving parts. It has a thin disk and a thick disk. It has an inner bulge and then the stellar halo, and all of these different parts have their own chemical evolution histories and accretion histories and star formation histories. So in comparison, dwarf galaxies are in some ways relatively simple, and so that makes them sometimes easier to interpret physically. But beyond just logistics, right, dwarf galaxies are useful from a physical standpoint as well, right? We know from lambda CDM, our best picture of structure formation is that it's the small galaxies that form first, and then over time build up into more and more massive systems. And so if we want to know how our Milky Way came to be, our own galaxy, we have to first understand dwarf galaxies and how they form and evolve. And then on top of that, if we look at the components of a dwarf galaxy, I think we can zoom in on sort of any single one of these components and see how dwarf galaxies are useful for answering sort of fundamental physics questions as well. So for example, if we want to know about the nature of dark matter, dwarf galaxies are dominated by dark matter, and that makes them useful systems to study. And the demographics of dwarf galaxies, their numbers, their masses, et cetera, all of those can help constrain our cosmological models, like lambda CDM. And then finally, dwarf galaxies, many of them are thought to be fossils of reionization. And so if we want to understand the early universe, a lot of those signatures of reionization may have been imprinted on the gas and stars in dwarf galaxies. So this is all great. Dwarf galaxies, they're great, and we love them. The biggest downside about dwarf galaxies, I think, is that because they're so low mass and they have such small gravitational potentials, they're strongly influenced by their environments. So inflows of gas, outflows of gas, I haven't really shown them here, but mergers, for example, all of those will have a huge impact on dwarf galaxies. That's relatively larger than the impacts that it might have on a more massive galaxy. And that can be a bit of a problem because dwarf galaxies, again, are low mass and low brightness. It's hard to see them very far away. And so as a result, we have a pretty biased view of dwarf galaxies. So by far, the single most well-studied sample of low mass galaxies is our own neighborhood, our local group. And the local group is excellent. There's, around 100 galaxies, dwarf galaxies in this local group, but that's still a pretty small sample. And it's also just one type of environment, right? If we look at the local group and compare it to all of the nearby types of environments that are available even in the local volume, for example, our local group is maybe I guess you could call it an average density environment, but you could also look at, nearby we have the Sculptor and Fornax clusters, which are much denser. The Virgo supercluster, for example. And we also have these large underdense regions, these cosmic voids that are close by. And so in many ways, our local group is potentially unique. And on top of that, it's not just the fact that it's on average, or an average density environment. It's also the fact that not only do we have the Milky Way, which is an L-star galaxy, we also have M31, which is another L-star galaxy very close by. And not all massive spiral galaxies, L-star galaxies, have companion L-star galaxies close by. And then on top of that, the satellite population of the local group might also be unique in some ways. So we have the LMC and SMC, which are relatively massive satellites. Not every L-star galaxy appears to have an LMC mass satellite. And so there's been a lot of work recently trying to study Milky Way analogs in other environments and the satellite populations of these Milky Way analogs. And there's some, disagreement about what those Milky Way analogs look like. But in general, I think people are finding that there's a huge diversity of L-star systems. So even among other L-star systems, our Milky Way might not be representative. And let alone if you start looking at these, broader different types of environments as well, like clusters and voids. So the good news is that, even though we've had this sort of relatively biased picture for a long time, we're beginning to push the limits. So with Gaia, we've begun to examine our Milky Way and its immediate neighbors in incredible detail, with incredible precision. And in the era of JWST, we're beginning to push to deeper distances, farther distances than ever before. So we're beginning to see some of these early seeds of Milky Way galaxies. And that's really exciting. There's already a lot of incredible science happening, but I think we're sort of missing a couple of steps. So especially when we try to compare these two regimes, we want to try to find a bridge between them. And the issue, I think, is resolution. So if we look, for example, near our Milky Way, if we're looking mostly at the local group that we've studied for so long, we have access to resolved stellar populations. And so with stellar spectroscopy, we can do things like galactic archaeology and making very deep color magnitude diagrams, for example. But that can only take us so far. So with sort of the current ground-based telescopes we can maybe get resolved stellar spectroscopy out to a megaparsec or so. With upcoming extremely large telescopes, ELTs, we're beginning to push that a little more, maybe out to 5 megaparsecs or so. And that's going to be incredible already. We'll be able to start looking at things like the Sculptor group, the M81 group, so different types of dwarf galaxies in different types of environments already. But it's still not a lot. So if we start comparing to sort of the massive multiplexed galaxy spectroscopic surveys that are ongoing, so this is an example from DESI. This is just 1% of all of the data that DESI have. And you can see that the resolved stellar systems take up this tiny, tiny fraction of the total number of galaxies that we could probe with, integrated light. So especially with fiber spectroscopic surveys, we can get tons and tons of galaxies, but they're all just blobs of light, and we're just getting light from some portion of the galaxy. And so it's a little better if you, instead of looking at spectroscopy, maybe you're interested in photometry. That's a little better. We can push resolved photometry a little further. There's a really nice recent result by Charlie Conroy looking at a low density stellar halo around a dwarf galaxy that was about 30 megaparsecs away. So again, we're already pushing the limits of what we have, and that's a lot of really cool science. But there's still a huge gap between what we can resolve and what we can't. And so I think it's really important that we start to bridge that gap in something that I like to call the resolution ladder. So it's an analogy to the distance ladder. As we calibrate the astronomical distances that we're measuring, we also need to calibrate the measurement techniques that we're using at these different distances. So we need to somehow bridge resolved stellar systems with, the integrated blobs of light that we see at high redshift. And on the observational end, I think IFU data is a really useful way to bridge this gap. So IFU, or integral field spectroscopy, is a good middle ground. So for example, if we compare IFU spectroscopy of galaxies where we also have resolved stellar measurements, we can do an apples to apples comparison and see what the effect is of doing a resolved versus an unresolved measurement. The problem is that this is still really hard. So even with a lot of new IFU instruments that we have, there's sort of this fundamental issue, which is that you want a galaxy to be close enough that you can resolve individual stars, but it has to be far enough away that you can fit most of the galaxy in an IFU field of view. And most IFUs are relatively small fields of view. And so as a result, I've combed the literature. It's certainly not a complete list, but I couldn't find that many of these studies doing these direct IFU and resolved star comparisons. And when I have found them, they've mostly been for individual galaxies. So for example, Leo A is a dwarf galaxy in the local group, and GC 147. It's a little better if instead of looking at individual galaxies, you look at individual star clusters. So star clusters are smaller in size, and so you can actually do this comparison a little more readily, but it's still kind of limited. And we're also sort of limited in the number of properties that people have looked at. So for example, if we want to measure the stellar mass of a galaxy or the dynamical mass of a galaxy, with resolved stars, you measure the motions of individual stars, and then you have to model. You assume something about the gravitational potential of the galaxy. You assume it's in virial equilibrium. You do some genes modeling, and then you get a dynamical mass. But at high redshifts, you're typically looking at velocity dispersions or rotation curves, and those are very different techniques. And I don't think there's been a direct comparison of kinematic measurements on the same galaxy with two different methods. So I think there's a lot of space for upcoming surveys and studies to sort of push on this particular rung on the resolution ladder. On the other end, if we want to use IFU spectroscopy to bridge to distant integrated light measurements, I think here the key issue, especially with spectroscopy, is aperture effects. So aperture effects are just when you have an aperture that's smaller than the size of your galaxy, and so you miss a lot of light. And this is not a new concept, right? Ever since the dawn of the first big spectroscopic surveys like SDSS and Deep 2, people have known about aperture effects and tried to correct for them. But for a very long time, a lot of this work has again focused on the most massive galaxies, which makes sense because a lot of these early surveys were mass incomplete, especially at the low mass end. And so recently, again, there's been, I think, a revival of some of these efforts to look at aperture effects and push to lower mass systems as we have these new IFU surveys, like SAMI, for example, which are beginning to probe the low mass end a little more. And so, again, I think this is a room to grow, a lot of things to explore here. And it's helpful because we do have a lot of ongoing IFU surveys that are starting to target dwarf galaxies in particular. So I've listed this, again, this is not a complete list by any means, but I've listed some of the ones that I happen to know about. So Sheila Kanapan at UNC is leading this Resolve/ECO survey, which is looking at relatively massive dwarf galaxies. So it's fairly mass complete down to the high end of the dwarf galaxy regime. So I should also preface this, all of these surveys are at what I would consider to be relatively high redshift. So I realize these numbers are very small to anyone who doesn't do local group stuff. But to me, these are like already quite large distances. And then there are also a number of relatively smaller surveys that are looking at dwarf galaxies in different types of environments. So the SAMI galaxy had a specific sub-survey looking at dwarf galaxies in the Fornax cluster, so a relatively dense environment. There's a MUSE survey that focused MATLAS, which focused on massive early type galaxies. And so there was some follow-up of the satellites of those early type galaxies. And then there's a survey that I'm the most familiar with because it's my survey. So the DIVE stands for Dwarfs in Void Environments. It's the only acronym on this entire slide that I actually know. But the idea is to look at dwarf galaxies in extremely underdense environments in cosmic voids. And I won't go into the details. There's already been a lot of great science from all of these surveys. I won't go into a huge amount of detail, but I do want to say that IFU surveys, not only can they help us address these questions about resolution and the effects of resolution on our different measurement techniques, but they're also just incredibly rich data. So we can get all kinds of information at the spatially resolved scale about, the kinematics, for example. That's what's plotted here, the stellar motions, the line of sight velocity and velocity dispersion within galaxies. We can look at the stellar population within galaxies, their star formation properties, their gas phase properties. And I think really interestingly, we can also start to do things related to intermediate mass black holes. So we can use IFUs to search for signatures of ionization from intermediate mass black holes in dwarf galaxies. So, okay, that's my quick spiel about IFU surveys. I think they're really cool, and there's a lot that we can do with them. But IFUs can only take us so far, right? They're time consuming compared to even traditional spectroscopy, let alone imaging. IFUs are, it's hard to take a lot of data, and then it's hard to reduce that data in a consistent way. And so the next best thing to do, if observations are difficult, we can always turn to simulations. And I'm an observer. I should preface this. I'm an observer, and so I fundamentally don't really believe in any single simulation, but I do think they're very helpful for testing things. We can test the effect of different types of physics on mock observations. And so that's something that I'm working on with a student, Azana Queen, and Sergio Martin Alvarez at Stanford. Our goal is to make mock observations from high-resolution hydrodynamic simulations of dwarf galaxies. And these are from the Pandora project, and they include a lot of different types of physics, so different radiative transfer schemes, the effect of cosmic rays, what else? Magnetohydrodynamics. And so we can turn off and on all of these switches and see the effect on mock observations. And so that, I think, is a really powerful tool. And again, this isn't a new idea. People have been doing this for more massive galaxies, but we're entering an era where our simulations can actually begin to resolve dwarf galaxies. They have high enough mass resolution that we can resolve dwarf galaxies on a meaningful scale. And so we can really start to do these kinds of mock observations for dwarf galaxies. And I think this, again, could be a very powerful tool. On the other end of the resolution ladder, we can use simulations to just test how well our methods for integrated light are recovering galaxy properties. So for example, with JWST, there's been a lot of SED fitting and a lot of back and forth about the mass of galaxies. But it turns out that a lot of the methods that we use to recover dwarf galaxy masses are based on assumptions that are maybe more appropriate for massive galaxies. And so as JWST and other instruments begin to look at low mass galaxies at higher redshifts, we really need to understand the different systematics that go into our mass recovery and our recovery of other galaxy properties. And so one ongoing project that I'm working on with Yasmin Asali, who's a student at Yale, we're taking simulated galaxies from a number of different types of simulations. We're making mock observations, and then we're comparing the true properties from the simulation with what we would get from applying different observational techniques. And so far, this is all very much in progress work, but so far what we're finding is that using photometry alone and empirical relations based on, for example, optical colors, a lot of dwarf galaxy masses get underpredicted by significant amounts. So this gray band here in the bottom right is sort of the order of magnitude 0.2 dex that a lot of people assume for systematic error when doing like SED fitting, for example. And we can see there's a pretty strong trend to underpredicting dwarf galaxy masses. And then if we use things like SED fitting, this is sort of the state of the art and what a lot of JWST results will use, for example. It also doesn't do that much better. So there's a strong systematic trend again for different types of SCD fitting algorithms, but there's a lot of assumptions that go into these SCD fitting models. So you have to assume something about the star formation history prior, the dust, etc. All of those are different knobs to turn. So this is all, again, in preparation. But I think it's very telling that, we don't even necessarily know how to recover the properties of dwarf galaxies in the local universe from SDD fitting or from other methods. And so I think it's really important that we understand that before we try to extrapolate to high redshifts, where we know even less about the conditions of the universe and the conditions in galaxies. Okay, so that was a lot, mostly talking about, the current state of the field and what I think could be done in the immediate future to advance dwarf galaxy studies at different resolutions. But this is a talk about habworlds. And so now I wanted to spend some time thinking about, what habworlds could do for dwarf galaxies. And so obviously the first thing is habworlds could observe more dwarf galaxies than ever before. I do want to say that, again, I'm not a space telescope expert, and so I did crib a lot of these figures from various LUVOIR and HabEx reports. So please correct me if any of this is incorrect. But it seems pretty apparent that habworlds will be able to sort of push the redshifts at which we can see the faintest dwarf galaxies, the true earliest seeds of the Milky Way, out to ridiculously high redshift. So we'll actually be able to see Milky Way seed galaxies in their sort of home environment, when for so long we've been limited to looking at local analogs. So that alone is incredible. It's really exciting. But on top of that, I was honestly shocked. I watched Jason Tumlinson's talk from last month, 2 months ago, sometime in the past. And he pointed this fact out, which was absolutely bonkers to me. This idea that because of the turnover in the angular diameter distance, dwarf galaxies in general could be resolved at any redshift down to 200 parsec scale. And that's absurd to me and incredibly cool. So not only will we be able to see, the early seeds of these Milky Way-like galaxies, we can actually look at within these galaxies, look at their substructure. And that I think will be very exciting. We'll be able to do a lot of direct comparisons with simulations that I think will test a lot of simulations and even a lot of basic galaxy formation theory at a level that we have previously never been able to do. So that I think is really exciting. But also on the resolution scale, since we've spent so much time talking about resolution, habworlds will push our resolution limits to sort of ridiculous levels. So we'll be able to do resolved, depending on how you define which stars you're looking at, but we can start to push spectroscopy and photometry of resolved stars out to 10 to 30 megaparsecs. And so that is, I think, for me, the most exciting question that I want to answer is whether or not our local group is special. And I think habworld's resolution limits, unprecedented resolution limits, will be able to really address this in a way that we haven't seen before. So there's a number of ongoing surveys that are really trying to address this question. We talked about this a little bit earlier, address this question about whether or not our Milky Way is unique. And so they're looking for Milky Way analogs. And there's been a bit of a back and forth between, it's not quite clear if Milky Way analog galaxies, if the satellites of those Milky Way analogs have quenched star formation or not. And a lot of it seems to be coming down to systematic differences between different surveys and the way that they measure different properties, so star formation properties. But with something like habworlds, we wouldn't have those issues, right? We could get deep star formation histories. We could measure the color magnitude diagram down to the main sequence turnoff of literally tens of Milky Way analog systems. So that would be maybe hundreds of satellite galaxies or more. And we could sort of address this question once and for all about whether or not our local group and the dwarf galaxies in our local group have unique star forming properties. And then on top of that, resolved spectroscopy outside of the local group is something that has not been done as far as I know, except maybe in extreme cases with, lensed systems. But if we were able to get spectroscopy for dwarf galaxies outside of the local group, we could begin to do really cool and complicated things like galactic archaeology. For galaxies in the local group, we've had these sort of I think, really interesting chemical evolution models that have been able to model in detail the exact chemical abundances of stars in local group dwarf galaxies. And that can tell us a lot about the evolution of the galaxies themselves. It can address questions about nucleosynthetic processes like type 1a supernovae or neutron star mergers. I won't go, I mean, these are from the results that I know best, which are my own results. But the idea that we could do this outside of the local group is sort of mind-boggling to me. The sheer sample size that we'd have in order to understand things like type 1a supernovae and whether or not, you know, the high or low mass type 1a supernovae produce high or low amounts of manganese and other iron peak elements. That's something that would be incredible to have. But of course, all of the biggest and most exciting thing about HabWorlds, and the thing that makes it really stand out from ELTs, like you could make the argument that a lot of the ground-based ELTs will have resolution that's not dissimilar to HabWorlds in the optical, but HabWorlds really adds this new component of the ultraviolet part of the spectrum. And that, I think, is where things get really exciting. So if we look at, there's a number of, you know, upcoming proposed UV CubeSat and medium-size missions. And one of those, you know, UVEX and other ones, including Ultrasat, will do all-sky UV surveys. And UVEX is predicted to detect on the order of tens of millions of UV luminous enough for UVEX to detect within 100 megaparsecs. And that is really exciting, partly because, especially, so surveys like Roman, instruments like JWST, because they're wavelength limited to optical and infrared, it's difficult to differentiate between high and low redshift systems because you want to distinguish between the Balmer and the Lyman break. And with the UV, you can do that. So no more degeneracy between high and low redshift systems. So UVEX will already be great for this with their all-sky survey, but HabWorlds might have, you know, a magnitude limit on the order of, you know, 100 times deeper than UVEX. And so with this much deeper UV sensitivity, HabWorlds won't be able to do an all-sky UV survey, I don't think, but it could do a wide survey. It could, with you know, tiling around strategic locations, like for example, around a Milky Way analog, we could start to find even lower mass systems than what UVEX will be able to detect. And then on top of that, UVEX is also expected to find the direct analogs to high redshift galaxies, so really young and low metallicity galaxies. And as shown here in this really nice plot from the UVEX white paper, so far, HST, again, because of its wavelength cutoff, is unable to really probe this extremely low metallicity young stellar population parameter space. And so UVEX is expected to detect, you know, thousands, tens of thousands, hundreds of thousands of galaxies in this discovery space, which would, again, be really direct analogs to high redshift galaxies. So UVEX will start to do this. And again, with their all-sky survey, they'll be able to find a lot of these systems and get integrated spectra. But HabWorlds will not only have integrated spectra with this proposed LUMOS. I'm not actually sure if this is still in the works for HabWorlds, but if HabWorlds had a LUMOS-like multi-object spectrograph, HabWorlds would be able to cover not only the galaxy itself, but its entire immediate environment, looking for things like outflows maybe, which could be really cool. But it would also get spatially resolved spectra as well. So I don't know if you can see, you probably can't because I don't think PowerPoint resolved the slide. Let me zoom in a little bit. That's the size of the sub-arcsecond microshutter that I think was proposed for this LUMOS instrument. And so HabWorlds would be able to get incredible spatially resolved detail, and that could tell us a lot. So UV spectroscopy can tell us about metallicities, for example, star formation rates, and in particular burstiness of star formation. So because UV traces different timescales of star formation than optical tracers like H-alpha, we can learn a lot about the timescale of star formation on these incredibly resolved scales within these extreme dwarf galaxy systems. We can also learn things about, you know, stellar winds from extremely massive stars, which can only be traced in the UV. So there's a lot. I won't go into a huge amount of detail here, but I think there's a lot that can be done. That HabWorlds will really bring this entirely new dimension to these upcoming UV surveys. And then zooming in even further within dwarf galaxies, UV coverage could also do a lot for resolved stellar populations. So I really like this slide. This is, I think, from one of the Habex science talks. Ian Roederer put this together, showing in the optical, we've found a lot of what seem to be very low metallicity stars. So here's an extremely low metallicity star. But even though, because of there are more metal lines in the UV, it's been difficult to distinguish in the optical alone the overall metallicity of some of these extremely metal poor systems. But with the UV, we could start to see UV metal lines, and that will really help us determine what are the true population 3 stars, if there are any nearby. And even if there aren't, low metallicity stars in general have a very big effect on chemical evolution models when we do chemical evolution model fitting. And so even just measuring more of these low metallicity stars and having precise measurements for their metallicities from UV spectra that alone would be sort of groundbreaking, I think, in many ways. And then I won't go into this because I don't know as much about these things, but we could also look at with the Habitable Worlds resolution, we can start to measure properties of binary stars or extremely massive stars. And those are incredibly important for things like the stellar IMF or stellar model library. So if you want to do any kind of galaxy modeling or SED fitting, you really need to understand the properties of binary stars. And we don't know those yet, but Habitable Worlds could begin to separate individual binary systems out to the distances, like in the Magellanic Clouds, out to M33. I think that could be incredible. Okay, and then some other thoughts. So I will preface this slide by saying I am absolutely not an expert in the things that I will talk about on this slide. I am operating on pure vibes, but here are things that I think would be really cool to see. And I think Habitable Worlds should be able to constrain some of these problems. So the first is measuring the IMF. I think there are a number of white papers about this already, actually. But on the stellar scale, the resolution of Habitable Worlds will vastly improve on Hubble's current resolution. And so we'll be able to do direct star count measurements, especially of massive stars that are most visible in the UV, in dense clusters where previously crowded field photometry has made that really difficult. So we'll be able to measure the stellar IMF, I think, in parts of the Milky Way and in the LMC and SMC in different environments that have previously been inaccessible entirely. And then on top of that, there's some work that suggests that on the galaxy scale, UV spectroscopy of galaxies can rule out extreme IMF variations. So if we want to understand the initial mass function, I think the UV is really necessary at this point. And then finally, this is perhaps pure wild speculation on my point, but I personally would love to get stellar ages from astroseismology outside of the Milky Way. I realize that the issue here is having really long baseline measurements. And so maybe Habitable Worlds is not the right instrument for that. But, and again, I'm kind of spitballing. It's possible that with OB stars, like really massive stars that are brightest in the UV, they might have high amplitude variability in the UV that is on timescales reasonable enough that we could actually measure modes and do astroseismic measurements. And if we could get precise stellar ages of stars outside the Milky Way, like even in nearby the closest dwarf galaxies, that would be incredible. I think we really need precise stellar ages to validate a lot of our chemical evolution models. And I think astroseismology would certainly be one way to do that. And again, Habitable Worlds might not be the right instrument if we need long baselines, but I think there have been some measurements with Hubble's guidance sensors in the past. Like people have done astroseismology using Hubble's guidance sensor. And so maybe we could think about ways to strategically use maybe not the Habitable Worlds main instruments, but some of these auxiliary instruments to do this kind of measurement. Okay, but again, this is I'm not an expert in any of this. I'm absolutely spitballing. But to summarize, I think Habitable Worlds is just going to be incredible for dwarf galaxies. I'm especially excited about increasing the sample of resolved dwarf galaxies so we can really build and calibrate this resolution ladder. And the UV will add so much. We'll be able to study more about galaxy properties and stellar properties that have previously been inaccessible at optical and infrared wavelengths. And there's a lot of prep work that I think needs to be done. Obviously, we need to build the instrument, but also a lot of prep work on the science side. So using IFU surveys to continue building the resolution ladder. A lot of the IFU surveys I talked about before are looking at things at, again, what I consider to be kind of high redshift. So out to, things that are at minimum maybe 50 megaparsecs away. So if we really want to make sure we're within the Habitable Worlds resolution limit, we need to start maybe doing tiled observations of dwarf galaxies within this 10 megaparsec regime. And then again, a UV mission like UVEX with all sky imaging, I think is really important in order to find interesting targets for Habitable Worlds to then improve on with its spatial resolution and much deeper UV magnitude limit. All right, that's, I think, everything for me. Thank you so much. It was really exciting to get to learn more about all the potential of this exciting mission, and I'm very happy to take questions, although I have no guarantee that I will be able to answer them.
Bravo. Congratulations. This was an excellent talk. Thank you so much for sorry, I always have to have that nervous moment in the middle. It's like, wait, am I muted? I have questions, but I'll open up it to the room first. But thank you so much for the wide-ranging topics. That was exactly what we wanted. Like you say, spitballing a few times, but that's fine. That's perfectly fine. We're decades out from habitable worlds. Starting to think about these things is exactly what we want at these sessions. So anybody else have a question? Otherwise, I might jump in. Okay, I'll start with this. I start actually with the last one, which is the where you talk about the astroseismology. Mm-hmm. So you need really long baselines. This is something that I know even less about. You introduced the topic to me, right? So, okay, I've never heard of any of this, but Habitable Worlds is primarily a exoplanet. Like some of the tech specs are very much driven by what we need to do in order to get spectroscopy of some very small dwarf rock around a star. So really high stability, the high precision, that is exactly what you would need for this, I'm guessing. So it's already good for it, but you said long baseline. What is a long baseline in this?
Right. So I mean time-wise, right?
Yes. Yeah. Like how long?
On the order of weeks to months is what I was told when I asked. At one point I asked an astroseismologist what it would take to do this with Hubble, and the answer was Hubble has the resolution to start pushing out to the LMC, but it would need to observe a star straight. It doesn't quite need the spectral resolution, but it does need. You really just need a light curve. Mm-hmm. But you have to be able to stare at the same star for on the order of weeks, which seemed a little unreasonable with Hubble and maybe also for Hab worlds.
So it's the kind of thing where you need, but the coverage is like, you can't do this with, I've looked at it for weeks, but I looked at it once every day. It has to be a high time resolution.
Yeah, it also has to be high cadence in order to, it would depend on the mode that you're looking at, I think. My understanding is different astroseismic modes will cause variability on different timescales. And so maybe, I don't know if there's been a ton of work because astroseismic measurements have so far been limited to the optical and infrared. I don't know if folks have identified modes in the UV, modes that would cause variability in the UV. And I don't know if there are estimates out there of the timescale of such modes, but it's possible if you could get a large enough cadence, a large enough period.
And short enough cadence, like so that they can match up. Because we've got, Galax has some time variability information, so it's in there somewhere. But then people look at Galax data and become sad because it's dead now. But one of the things that Habitable Worlds will end up doing is essentially stare at a Milky Way star for a very long time. So this is the kind of thing like, hey, this could piggyback. You said something about the guidance sensors. That would be for the guidance star, which is by definition a Milky Way one. But if you have, I don't know, a convenient dwarf galaxy in the back, and it's taking spectra for literally thousands of hours, you could be doing this depending on the readout modes of the instrument, right? So if the instrument has a timing mode that it times how often when the photons come in, that would be a reasonable reason to do this. If I'm looking at this planet anyway, it's like, is this something that I could do in parallel?
Right, exactly.
And that said, I mean, if it's a month for something that's a period of weeks, I mean, that's what Cepheids are. Like we stare at Cepheids with Hubble all the time, but apparently those are the wrong big blue stars. So
I think so. And I think you would, and I think in order to do any of this, I think there would have to be more work on the theory end to identify modes first. Like that has sort of, my understanding is that's been the big challenge with astroseismology is, Kepler and TESS have had tremendous amounts of optical data, time variability data, but the challenge is on the theory, like actually identifying which variations are caused by which modes. I think that has been the challenge. I don't know how much of that is feasible in the UV and how much of it has been done in the UV. So that might be something to explore along with the instrument feasibility. But I agree. I think that's what was done with Hubble's fine guidance sensor. I think during one of the periods where Hubble was just staring at something, they had this fine guidance sensor just counting photons and recording them as a function of time for some other target.
So we talk about AGN variability as well, and that's why I know that there is a variability option on Galaxy. I'm just not sure if anybody else actually looked at those.
Yeah, no, I haven't looked at those at all. That would be really interesting.
So I know there is time variability studies are possible with Galaxy, but that's it. Like, end of my information. The second one was about. I have a second question about the stellar masses. So the 0.2 Dex, I was so happy that at least I didn't have to worry about stellar masses. We got stellar masses licked. That was the feeling for such a long time. And then your plot made me go, oh, not so much. Because, the deeper surveys are now pushing into that dwarf galaxy regime, right? We're getting those from where we have now the spectroscopic redshifts for 10 to the 8 solar masses. Galaxies are starting to pop up in deeper surveys. So it's kind of, we've been counting on this 0.2 Dex, we can get it, whatever you get out of your SED, your stellar mass is good enough. And that clearly is no longer the case. Like there's clearly an inflection point around 10 to the 9 where I should not trust them anymore to that level. And we're back to the 1990s where it's like, it's somewhere in the order of magnitude.
Right. And, if you look here, the prospector it stays kind of within the 0.2 Dex range, but there is certainly this trend. And I've been trying to figure out where this comes from. I think it has to do with the stochasticity of dwarf galaxy star formation histories. So once you start having multiple bursts, it becomes very difficult, even for something with a flexible star formation history prior, right? There's no such thing as a truly non-parametric star formation history prior. You have to assume something about the bin sizes that you're looking at. And I think that's the difficulty. There just aren't, it's possible that UV could help actually with this, because again, UV is sensitive to a different time scale of star formation. And so mostly I've been looking at optical and infrared photometry here because the current interest is with JWST, but it is entirely possible that adding UV will actually improve these stellar masses for dwarf galaxies.
Yeah, we have been finding that. So there is a small UV capable satellite called Swift, and you can do things with that. And it has it's only in the NUV, but it has narrow filters there. And so you get more finely sliced wavelength information. And so we're finding that, or at least our guess is at the moment, we're not quite there yet, but that the most recent star formation history direction is sort of indicated by that color. But that is star formation history. Like, I don't know, I'm still sort of trying to get the idea through my skull that's like, but if I just use a mass to light ratio of 0.6 and I use the WISE W1, I'm probably fine. That's what.
Right. Well, I think again, the star formation history does play a role there, because if you're assuming a relatively constant or even constant-ish star formation history, but the true star formation history is bursty, you can hide a lot of low mass stellar mass.
It's area under the curve.
Exactly.
Okay. Yep. That explains why Seagal is doing such a job.
Yeah,
there.
yeah. And to be fair, we haven't played a lot with the assumptions that go into Segal yet. One thing, that's the big thing, is like Prospector and Segal, all these SCD fitting models have so many knobs to turn. And people will turn them differently without, and I don't know if we fully understand, especially in the dwarf galaxy regime, which knobs are even reasonable to consider turning.
All of them, I think. So yeah, but yeah, no, we keep running into this, like, oh, the dust model is also, that's the one for big star forming galaxies. There's no reason that that would be valid in dwarf galaxies all the time anyway. So it's, yeah. Oh, there's a question, like, how are you generating the SEDs for the simulations?
Yeah.
So where do these come from?
These are extremely simple mock observations. So we're basically, from the simulations, we have star formation histories and chemical evolution histories, and we plug those into FSPS, so flexible, and then so it's not a full radiative transfer model by any means. I think that would be the next step, but this is sort of, so Prospector is based off of FSPS, and so in some ways this is really a recovery test. Can Prospector get the right answer assuming the same kind of model?
So we do have lots of photometry collections already, where the photometry is fine, but you can compare the different SED fitters, for example, and just say like, okay, I'm just being agnostic on what SED. Sarah has something in the comments on the IMF as a measure in the UV. All right, yeah, let's go there. I'm happy to follow up on SEDs later, but you know, that's
sorry, let me just quickly skip to the IMF. Okay. Yeah, Sarah, I'd love to hear your thoughts. I'm, as I said, I'm very much not an expert on this.
I will read off the questions if people just want to type them in there. She's here. Comment and or a question. I'm excited about the direct stellar populations. I mean, we worked with that with Hubble, and you can do that up to about 40 megaparsecs apparently with JWST, but that's only good for AGB stars and RGB stars. So yeah, that's sort of dealing with giants, but everything on the blue end is just blue, and then you ignore it. So it'd be very interesting to see what actually is happening on the main sequence.
Oh, I finally got my voice. I've been working with the University of Geneva and Yvonne Hubany on making simulations of bursty galaxies of low metallicity, low mass galaxies or clusters. And I was trying, some of the simulations showed oxygen 4 in the UV. Very exciting because it looked like they were rotating very rapidly. And I looked in the simulations to see where the oxygen 4 was formed, and it's between 20 solar masses and 120 solar masses. So then I thought, I can find out about the IMF. And I changed the value of IMF of the saltpeter IMF minus 1.35. I changed it, and it didn't make any difference.
Really?
And I thought, what am I doing wrong? Well, I was thinking wrong. The low mass stars don't emit in the far UV. And so the range of 20 to 100 20 to 120 isn't very much. And that's why I saw little to no change in the
I think that's fair. I mean,
so it's just a warning don't
be
like
it's one well taken. I think so that was true even in the extremely low mass, low metallicity systems also, because there I would expect, the effect of a single massive star, because everything is so stochastic that a single massive star, even if it's just one, could have a huge effect. Like I could see how that might get
yes,
into that
in the far UV of the it's produced only by massive stars.
Right. Okay. I think it would be good to follow up. I'm not 100% sure if I'm following the exact result. Would you mind chatting about this later?
Yep. Oh,
okay.
yeah.
I might have lost. So...
Yesenia has also a question. I see a hand there.
So thank you very much.
Oh, thank you, Sarah. Yesenia, I don't know. I can't hear your audio. I'm not sure if that's...
Did I just mess myself up?
Oh, there we go. Okay.
Hey, okay, hi. So this is gonna be a really basic question compared to everything that y'all have been speaking about. I have a geology background and I'm working on science communications for Habitable Worlds right now, which is why I'm attending this session, because I'm trying to understand the astrophysics side a little bit of it, because I deal with rocks. So basic question about your slide where you were talking about the things that you were excited about. When you're saying about characterizing metal poor galaxies, so why exactly are we excited to find metal poor galaxies? Like, is it because they're younger? What does it tell you in general? Like, why is that
no, it's a good question. So we think that metal poor galaxies, so in the very early universe, there were no, when we say metals, right, as astronomers, we mean anything heavier than helium. And so in the very early universe, there were essentially no negligible amounts of metals at all. And so the first galaxies and the first stars to form would have formed out of this very, very metal poor material. And so we think that the most metal poor galaxies in the local group, like maybe not in the local group, but even close to us, will be direct analogs of the very earliest galaxies. Oh. And this search for what are called population 3 stars, these are the most metal poor stars. They're thought to have essentially zero metals at all. And those would have been population 3 stars, if they're still surviving today, would have formed from that very first generation. They would be from that very first generation of stars.
Okay, suddenly I understand why that's super exciting. Oh my gosh. Yes, that sounds amazing. I'll probably look a little bit more into that. Would you mind if I could send you an email maybe if I had any other questions? Okay, that's really great. Thank you so much.
Cool. We love crossing interdisciplinary borders.
Great. If no other questions, Benny, shall we wrap up? Looks like you're muted. You're muted.
I was thanking Mia and saying, yes, we should wrap up. And I said that was 5 minutes. And yeah, okay. All right. I'll be the elderly professor here. So thank you so much, Mia, for an excellent talk. This was really good. It's exactly the kind of thinking that we want to get from people, and have people start thinking about habitable worlds, right? If your input right now means that sets design requirements, you saying, hey, we need this from theory, means that we can push a theorist to go give us an answer so that we know what cadence we need, and that cadence will drive what we're going to ask the engineers. And so now that's excellent thinking. So well done. Thank you so much. And,
thank you so much. This was really fun. I'm so looking forward to getting to know more about space telescopes in general and Habitable Worlds in particular.
Oh, this was an excellent talk. So good, fantastic place to start. Okay, thank you all for coming. Thank you all for the wonderful questions. Yeah, bravo to Mia, and we'll see you in a month's time. Or we have a theory talk. We swap them out. So
sounds good. See you next month. Bye.
Thank you.
Bye.